with falsehood and negation. So the idea here is that we want a way of sort of summarizing that something's not true. And we saw before in the earlier chapter that if you can basically introduce a falsehood, then you can prove anything, basically. And so the way that this is sort of enforced in COC is to say, well, if you can take a proposition P and prove false from it, then you can sort of consider that P is not holding. Okay, and so this is quite a constructive view of falsehood. In the classical logics that we might do in sort of maths classes and things, we need to know that basically a proposition is either true or false, and it can't be anything else. Whereas in this sort of setting, it could hold, in other words, we could prove it, or it could not hold, in other words, we can prove false from it, or we might not know. And the reason that we don't know is we just don't have a constructive actual proof of the thing, or a constructive proof of not the thing. So in these sorts of systems, we don't really need to introduce anything new to do negation of properties. We just think of it as an implication of this form, which is essentially a function that takes a proof of P and computes a proof of false. So in COC, they use the tilde notation for not as a shorthand, and you can see from the type here that not is a prop to prop. So it takes a proposition and returns another proposition which represents the argument proposition not holding. Okay, so you can also think of it, so this one is this is the theorem that says from false you can prove anything. So notice that the argument P is some arbitrary proposition, and the theorem is, well, if you know false, then P you must have a proof of P. So that's easy to prove in COC. So I can introduce these things. Notice that we've used the name contra for the thing that we know is not ever going to be possible. So for contradiction, so contra is a proof of false, and if we destruct that, there can never be a proof of false. That's one of the constructive sort of premises of the whole system. We can destruct it. And so that says basically, well, if I've assumed that such a thing exists, then I can prove anything because that such thing can't exist. Okay. So this is sort of two different directions, right? So if I have false, I can prove anything. And the not is saying, well, if I know P, I can prove false, so hence P logically doesn't follow. Okay. So we can do sort of proofs like this. So for example, this is a theorem that says for any proposition, if I know that not P holds, then for any other proposition, I can show that P implies that thing, right? Because P not holding is effectively equivalent to false, and we know that from false we can prove anything. So how would we actually prove this theorem? So we do the intros. So we want P. The next one is not P, right? And the next one is Q. So we can introduce all of those. And what we want at this point is we want P implies Q. Okay, so what have we got? Well, you might say, well, let's introduce, so let's add to that a little p, right? So little p is a proof of P, right? And if you notice, not P, what we've really got here is P implies false, okay? And so some people do, so one thing that's quite useful to do in here is to unfold the not to make it obvious that that's the case. Some people would unfold not at the beginning before they do all the intros. That's you'll see that in a bunch of these proofs. So now we have something interesting. So we've got P, which is a proof of P, and we've got a theorem that says if P is holding, then false happens. So we can do something like, this should work, apply not P in little p. So now we've got a proof of false in our assumptions, right? So one way of discharging that would be to just destruct on P, because P cannot, little p of type false can't exist, so we can destruct on it to get rid of it. Another one that you can do, I think, is contradiction. No, that's not, oops, can't type properly. That's a contradiction tactic. We'll go looking for things that don't follow in the assumptions, which makes the proof a little less dependent on names and so on and so forth. So the key thing here is really the unfolding of the not, because if you sort of work, once you get used to the idea, it's not too bad. But if you see the tilde here, it's a bit non-obvious what to do next. But as soon as this turns into P implies false, then it's much clearer how to proceed. Okay, so we can also use, so once we've got any proposition, we can negate it with not, right? So here we can say that it's not the case that 0 equals 1, right? And again, notice the notation that it's doing here. So it's using the old school not equal to symbol from programming languages. So that means not equals. And it's inferred that from the not equal here. So the theorem uses the slightly more verbose syntax, and the system has worked out that that's equivalent to this one. So if I did an unfold not here, you see we've got exactly what we would expect, which is that 0 equals 1. Oops, don't do that. 0 equals 1 implies false, right? Which is exactly what not 0 equals 1 means. And so what the proof does here is it introduces the 0 equals 1, which we know can't be the case. So we call it contra, and then inversion on contra gives us the final thing. You don't need to unfold the not, because the intro's contra will do that for you. So it's equivalent to that proof there. Okay, and that's just confirming that if you use the less than greater than symbol, that's a proposition as well. Less than greater than, I think, came from Pascal or earlier languages from the 70s and 80s. So you don't see it too much. Mostly you get the not equals like this, which is what C introduced instead. Okay, so this is just a proof of the same thing using the not equal to notation. So these examples here are mostly just for practice, but they're basically saying that, you know, usually what you want to do is unfold the not to start with. Okay, so in this case, here's a proof of not false. So if false is the thing that we can't prove, then it should be the case that not false holds. So if we do this, what do we got? Well, we've got false implies false. All right, so the first false is the one that the thing we're sort of assuming, and this is the, well, we've got a contradiction sort of thing. And again, I can just introduce a false, and then there cannot, H can't exist because it's of type false, so we can get rid of that. Okay. Another one, so the name of this is very descriptive, right? So if we have a contradiction in our assumptions, we can prove anything. So if we take two propositions and set up a contradiction where we know P holds and we know not P holds, Right? Remember the conjunction from before. We know both of these things hold. Then we can prove Q, and Q is just some arbitrary other proposition. Okay, so the intros here is going to do P and Q, but it's also going to set up names for the pieces of this conjunction. So HP is going to be a proof of P, and H not A. I don't know why it's not A. I think it should be really not P. Let's change those. It's an old version of the theorem. So if I do that intros, I get P and Q, I get a proof of P, and I get a proof of not P. Okay, and I want to prove Q. So we can basically use these two here to derive false in a similar way to the previous one. So we can unfold the not, so we know we've got P and P implies false, so we can apply one and the other, and now we've got HP as a type false, so it can't exist, so we're done. Okay, so that gives sort of a flavor of the sort of proof. I won't go through the double negation, but you can imagine that if you know P, then you know not P. Okay, turns out the other direction is quite a bit harder to prove in COC, but we won't discuss that at the moment. Things like contrapositive, so these are again sorts of theorems that you get in logic courses when you're talking about Boolean logic or whatever. Let's see, not both true or false is a homework, I think. Yeah, and there's a couple of others that you can try on your own. I'll go through those ones. Okay, so that's negation. So basically negation is not a new thing. We've got the notion of a proposition holding in the system, and if a proposition implies false, in other words, we can derive false from a proof of that proposition, then we say that the proposition is negated or is not true, and we can do inequalities and things as we saw. So the next topic is truth. Now, we might sort of imagine that truth is just, the dual, if you like, of false. Turns out in a system like COC, knowing that something is true is not terribly interesting, right? It turns out that in this system, there's a type true, and there's a single value I of that type, which we can use to prove true. So this is a very easy proof here. The true is true. It doesn't really require us to do anything except use the I that we've already got, right? So why is this interesting? Well, it's not really interesting, that's the point. So you almost never use true as a proposition. You're interested in whether other propositions hold, which is not the same as them, really the same as them being true. But true is sort of a trivial proposition that always holds. And it's not very useful. There are, as the text here says, there are a couple of cases where you need a prop to sort of fill in some place in a theorem or something. And so sometimes you do want a proposition that's sort of trivially true. So you can use true for that. But we won't use it very much at all. All right, so what about logical equivalence? So this is essentially what mathematicians would call if and only if, right? And essentially, like in the mathematical setting, it's just a situation where you've got two propositions and you've got an implication in both directions between those propositions. So we've got the conjunction here, so both of these hold, and P implies Q as well as Q implies P, okay? So if we've got that, we say that that's P if and only if Q, right? So if is one direction and only if is the other direction. And this notation here with the double-headed arrow is a pretty standard way of writing if and only if. Okay, so again, there's nothing new here, right? This is just a conjunction, which we've seen before, and implication, which we've seen before. It's just a shorthand notation for the combination of those things. So when you're doing proofs on it with them, as long as you understand what the shorthand notation means, you can reason about them, but they're basically proven in the same way as we normally would do. So for example, this one says that if and only if is symmetric. In other words, if I've got P if and only if Q, then I also have Q if and only if P. Right, we can swap it around. So what's the intros doing? So it's going to give us P and Q, and then HAB, which I think, again, this really should be PQ, QP. It's going to be Q, just to stick with the same names. Okay, and so the stuff in square brackets, again, like before, is going to match the two components of this, which is, remember, it's an AND. Right? So you can see that the two pieces of the AND will get names. Sometimes, if you're still sort of a bit confused about what this is going at, it's useful to intros the first part and then do an unfold if and only if, and then you get the fully expanded version. So you can see quite clearly now that the next thing you're going to intro is an AND. Okay, so you can, so it'll work. So you can do intro like that. Oops. That's not going to work like that. I have to do intros like that. Okay, but we don't need the unfold. We can do all of that in one step like this. Okay, so where are we now? So we're at the point where we've got two propositions. We've got a theorem that says that if we know P, we know Q, and another one that says if we know Q, we know P, and we're trying to prove Q if and only if P. Now remember again, the if and only if is an AND, so we can split the goal here. All right, and now we get two goals that handily turn out to match the things we already know. So we already have a proof of Q implies P, right? And we also have a proof of P implies Q, so we can just apply those to easily. So essentially what this is just doing is taking a conjunction, unpacking it, and swapping the two pieces of the conjunction around and putting them back together again. That's essentially what's happening in a programming sort of sense. So you can prove a whole bunch of other things like, so this is one sort of technical thing that you want to be very clear about is the difference between false and true with capital letters starting them and false and true with lowercase letters starting them. And the latter ones, like this, are Booleans. And Booleans and true and false propositions are not necessarily the same thing, right? The Boolean is just a value you can calculate with, and a proposition is a sort of logical thing that the system knows about. So this particular lemma is about, if I know that a Boolean is not true, then it must be equal to false, and in the other direction as well, because this is an if and only if. Okay, it's not got, these are not the prop true and false, they're the Boolean true and false. So that proof is pretty easy, I won't go through that one. You can prove some properties of if and only if. So this one, P, so if and only if is reflexive, which means it holds between a proposition and itself. Okay, and I think you'll be able to see how that works. So this is really two lots of P implies P's, right? And if you've got one P implies P, you've got the other one. So that's pretty straightforward. This one I think is a homework exercise. So this is just saying the obvious sort of transitive property of if and only if. So P if and only if Q, and Q if and only if R, then P if and only if R. It's proved in a similar way to this, just pulling it apart and putting everything back together again. I won't go through this one either, but the simple sorts of, so this is a distributive law from logic about or distributing over and. So you can prove that that holds, and you can, because it's an if and only if, you can prove that it holds in both directions. Right? Doesn't matter which way you go. And this is a bit of a subtle point, which we won't worry too much about, but there's this library. We know we can do rewrites when we have equalities, but this library also means that you can get rewrites in other sort of equivalent situations. So in the case of an if and only if, you could say that if I know P, if and only if Q, then it's safe to rewrite P's into Q's and Q's into P's. And that's essentially what this library will give you. So an example of that usage is down here somewhere. So if I do this one, no, it's not that one I want to do. Yeah. So just get this to, right, so here I've got this theorem from up above, mult 0, which says if I've got two numbers and I multiply them by 0, then it must be the case that one of them is 0, maybe both, and this is an if and only if, right? So down here I can use rewrite with that, and that basically looks, if I'm going in the left to right direction, it looks for things that match this pattern, n times n equals 0, and rewrites them into this pattern. Okay, and probably does some simplification and stuff as well, so we can see what this looks like. So see here where we've got something or other, keep that on the screen. We've got something or other times P equals 0, right? So if I do the rewrite, I've now got, well, it must be that something or other equals 0 or P equals 0. Okay, and if I do that one more time, I'll get the n times n. Right. Right, so now I've got n equals 0 or m equals 0 or p equals 0, which is what we want for the n times p equals 0. And that's essentially what we have over on the right side, except the associativity is wrong. So you can see the brackets here. So the or sock fixes up the brackets or introduces them on the other side, and then we're done. So the only new thing here is that these rewrites are using a theorem that's not an equality. It's an if and only if. But you can, once you've imported this setoid library, you can do that with if and only ifs as well as the others. Okay, and the same with apply. So if you think of apply taking a theorem that says, you know, P implies Q, and if you know P, then you can get Q by applying it. And if and only if is fine as well, because it's really apply. It's really that in that direction as well as the one in the other direction. Okay, so in this case we're using that mult 0 backwards from the n equals 0 or m equals 0 up here to conclude that n times m must be equal to 0. So again, the apply is not a, the apply is using a theorem that has an if and only if in it, which is an implication as well. Okay, so again, there's a bit of notational stuff here. There's not a lot of new concepts. It's just more getting used to the notation, and the tactics are a bit more general. The last one that we'll do in logical connectives is exists. So when we've been doing lots of for alls before, so we've had universal quantification. So there's a way of saying, you know, for all natural numbers this property holds. Exists is the existential version of that. So it's not, some property doesn't hold for every such natural number. It holds for at least one natural number. So there is a natural number such that this property holds. So that's the sort of logical explanation. if we're doing this in COC, we have a theorem that looks like this. So the syntax is quite similar to the for all, except we say exists. Okay, but we treat, so if we had a for all here, we would be introing this variable, right? And what that does is it moves it to the top and it says, well, it doesn't matter what n's value is. But that's appropriate for universal quantification because we want the theorem to hold for any such n. That's not appropriate for exists because we don't want to prove it for any n. We want to prove it for a particular n. Okay, so the way this works in COC is if you have a goal that's an exists, you can solve that goal by telling the system which n is the n to use, basically. So sometimes it's called giving a witness for the existential. You're saying, well, the n that we want to use is this particular one. Okay. Now that doesn't, so in this case, you can use the exists tactic to say, well, 2 is the n that we want to use. So if I do that, it doesn't absolve us from showing that 2 actually works for the proposition, right? So this is saying there is an n such that 4 equals n plus n. If we'd said exists 0 or something, we wouldn't be able to prove this, right? Because 4 is not 0 plus 0. So we have to pick a good n, but we don't have to prove it for all of the n's. We just have to find one n. And that's the exists tactic is the one that lets us pick the n we want to use. Okay. And so that's what happens when we're using exists in a goal situation. So again, if we've got a goal that starts with exists, then we can nominate the value we want to try and use. This proof down here has a, introduce all those things. It has a what should I say? Let me do this in 2 steps. I just intro in. So notice that this assumption here itself is an exists. So what does that really mean? Well, that means that you're assuming that there's an m such that that holds. Okay. So what that will do when you intro it will, so I'll do this in a couple of different steps. So if we introduce, say h here, we get an exists up the top. And one thing I can say, well, if I have an exists up the top, there must be a witness. We don't know what it is, but there is a witness for this exists because we've assumed this thing. So one possible way of doing this is to do an inversion on h. All right, so in this case, it's called the witness x, and it's given us a theorem that says n is 4 plus x because this holds for our witness. Okay, so the name's not very useful. The version that they had sort of does all that in one intros because it's introing the name of the thing and the name of the property at the same time. So we end up with this. So m is coming from this intros, and we also know that n equals 4 plus n because of the exists. That's the assumption. Okay, so it takes a little while to get your head around this, but if you have an exists as an assumption, you know there must be a witness for it. If you have an exists as a goal, you've got to find the witness, basically. So that's where we are now in this proof. We've got to find a witness O such that n is 2 plus O. Okay, and looking at our assumptions, we can see that if we chose O to be 2 more than m is just some number, then this would turn into n equals 4 plus m, which we know. So you can see in the proof they do, well, let's pick 2 plus m as the witness. And then so basically what that does is just removes the exists and replaces O with 2 plus m. And now a bit of some simplification and use of HM is enough to solve the theorem. Okay, so practicing with exists is quite important because you'll find that you have to get into the swing of doing do I have a witness or do I need a witness? Those are the two sorts of cases. So this just exists or is the homework one. It's basically saying that if you know that there's an x such that px or qx holds, then you know that there's an x that px holds or there's an x that qx holds. So it's a distributive law, and in the other direction. So it's an if and only if. So you have to prove both directions. Okay, so we'll stop there and then we'll pick up with the last section in the next video.